Hello and welcome to the fourth video of the FP1 chapter, Complex Numbers. Starter question on the screen for you as usual. If you have time, go through this to review our previous work. Given that z is equal to 2 plus I, on an argand diagram represent these various complex numbers. So I'll start with the easy one, z. 2 plus I is about here. The next easiest, perhaps, is z star, the complex conjugate of z, 2 minus I. Z plus z star, z plus its own conjugate, so we have 2 plus I plus 2 minus I gives us a real number 2 times A, in this case 4, here. Next, z minus z star, which equals 2I, an imaginary number. Z times its own conjugate, gives us 4 minus I squared, which gives us plus 1, equals 5, a real number. And finally, z divided by its own conjugate. We have to multiply top and bottom by the conjugate of the conjugate, which brings us back to z. And we already know that the multiplication on the bottom gives us a 5. On the top we have 4 plus 4i minus 1, which gives us 3 over 5 plus 4 over 5i, which is quite hard to get accurately on my diagram, but it's about here. A little bit crowded, but there you go. In this video, we're going to look at modulus and argument of a complex number, which will lead us to the modulus argument form of writing a complex number. The complex number z can be represented as a vector. We looked at that in the last video, and we know that vectors have both magnitude and direction. This leads to an alternative way to write complex numbers. We have specific terminology though, because they are complex numbers. We call the magnitude of a complex number vector the modulus, and we call the direction of a complex number vector the argument. And obviously this is where the term modulus-argument form comes from. So let's look at where these are. If we have the vector z is equal to 6 plus 4i, then of course the modulus is calculated in the usual magnitude way and is written like this. In this example, we have 6 squared plus 4 squared is equal to the modulus squared. That gives 52. So our modulus is equal to 2 root 13. And obviously it's a positive because we're talking about the magnitude of the vector. The argument is all about the angle here, theta. It's measured from the positive real axis, but as we'll note in a few moments, it's not always measured counterclockwise, so we'll have to be careful of that. To calculate the value, we do it in the usual way as well. We know this distance is 4 units, and along the real axis the distance is 6 units, so the tan of theta is equal to 4 over 6, so theta is equal to 0.588 to 3 significant figures in radians. And the argument of z, written arg z, is equal to this angle. But while in general you can use the tan equals y over x to find theta, you have to be careful whether this is what is called the principal argument or not. And this is just an angle that is specifically in the range minus pi to pi. I'll go through the 4 different quadrants of the graph and quickly show you each of the angles and the arguments. So we already had this one here. If z is over here, then this angle here is theta, and the principal argument is theta. However, if we have a complex number in the second quadrant, the angle with the x-axis here is what you would probably get out of your calculator, call that alpha. But the principal argument measures from the positive real axis. The principal argument would be this angle, theta. In the fourth quadrant, we use this angle, and this is given as a negative angle because it's going clockwise from the positive real axis. Finally, in the third quadrant, you might be calculating this angle, but the angle that is the principal argument of the complex number is this one, measured clockwise from the positive real axis in order to be within this range. And you can see from the inequality symbol here and here that if your number happens to be on the real axis, a negative real number, for example here, then we give that the argument pi, not negative pi. So the argument of z is defined as theta, but you need to be careful which angle you're calling theta in your diagrams. And usually with my students, I urge them to draw a diagram. When we look at the modulus argument form, it's very easy to get the wrong angle unless you have visualized where your complex number is on the Argand diagram. So when I do that later in the video, you'll notice that I always draw a quick sketch of the Argand diagram. So here are some examples before we get to that. Given the complex number z is equal to 2 plus 7i, find the modulus of z. And even here I'm going to sketch Argand diagrams. So we've got the real axis, the imaginary axis, 2 plus 7i is up here somewhere. Doesn't need to be accurate, I just need to have a good idea of which angle I'm going to get from my calculation and which angle is actually the angle that I want for the argument of z. The modulus, of course, is a little bit easier. 2 squared plus 7 squared, square rooted the positive root. And that's equal to the square root of 53. Back to my angle, let me call this theta, because that is the argument that I want, and in this case, tan of theta is equal to 7 over 2. So I can get it directly from this calculation. Remembering to write it in radians, and in this case, the question wants 2 decimal places, which is 1.29. And there we have the modulus and the argument of this complex number. Another example, in a different quadrant, this is minus 4 minus I, somewhere over here-ish, where the argument is this angle, and the one I'm likely to be calculating is this angle, call it alpha. But first the modulus, that's quite easy. 4 squared plus 1 squared, which gives us the square root of 17. Tan of alpha is equal to 1 over 4, which gives alpha as 0.244 ... Therefore, the argument that I want, the size of this angle is pi minus 0.24 ... But because it's beneath the real axis, coming clockwise from the positive real axis, this will be a negative answer. So theta in this case is equal to negative pi minus alpha, and that is minus 2.90 to 2 decimal places in radians. Next we have a final example to verify a general result that is well worth remembering. Given z1 equals this and z2 equals this, find the modulus of z1, modulus of z2, z1, z2 as a complex number, and then verifying the result given. So the modulus of z1 is equal to 3 squared plus 4 squared square rooted. Pythagorean triple gives us a 5. z2 is also a Pythagorean triple, which gives us a 13. Part B, we need to multiply these two complex numbers in the usual way. And part C, we need to find the modulus of this result. Which is the square root of 63 squared plus 16 squared. Putting it on my calculator, I get 65. And the very last step to verify the result is to state quite clearly that 5 times 13 equals 65. So we have not proven it, but we have verified that in this case this result is true. And without going through the proof, let me state for you that this is always true. It is a general result that you can use and quote without proof. Okay, we're about ready to look at the modulus argument form of a complex number. Because we know how to get the modulus, we know how to get the argument. These are from here. The magnitude of the vector and the angle from the positive x-axis in that given range minus pi to pi. What we also know is the general form of z equals x plus iy. Now it looks a little bit different to what I've used so far. I'm using x instead of a and iy instead of bi, just because x and y are connecting with the coordinates on something that looks like a graph. Don't let that put you off, it's the same thing. And this helps us to understand the connection with what I'm about to say, because we also know that the x-coordinate on a graph is equal to the modulus, or the magnitude of this, multiplied by the cosine of the argument, or the angle here. And the y-coordinate is given by the modulus times by the sine of this angle. So we can write this in this form, where r is equal to the magnitude of the vector, or the modulus, and theta is equal to the angle, or the argument. R here, the same r, and theta here, the same theta. For convention's sake, we take the r out and we factorize this to give the modulus argument form here in green. So if you're taking notes, write this down. The modulus argument form of a complex number z is given by this. Z is equal to r times cosine theta plus I sine theta, where r is equal to the modulus of z, and theta is equal to the argument of z. Strictly speaking, it does not need to be the principal argument of z to be in the modulus argument form, but that is usually the argument we use, unless told otherwise. A quick note here as well, if you need to go back to the x plus iy form, I hope you realize that's actually quite easy. If you know r and you know theta, you simply put r times cosine theta onto your calculator, and that gives you the x-coordinate. In the same way, r times sine of theta gives you the y-coordinate, and you just remember to put the I in there, and you're back to the previous form. So our final couple of examples are putting complex numbers into modulus argument form. Express this complex number in the modulus argument form. And here they're specifically stating it needs to be the principal argument. So I can't say this enough. Start by sketching a diagram. This will ensure that your angles are correct in your head as to which one you need and which one your calculator will give you. Minus root 3 plus I is somewhere over here, say. So the modulus of z is equal to root 3 squared plus 1 squared square rooted is 2. And the argument of z is this angle here, although my calculator is likely to give me this angle alpha. And that is pi by 6. So my theta, which I can see from the diagram is going to be a positive number, is pi minus pi by 6, which is 5 pi by 6. Putting these two together into the correct format then, we get z is equal to 2, which is the modulus, times the cosine of the principal argument 5 pi by 6, plus I times the sine of that same number. Now I realise that might seem a much more complicated way to write the complex number, but at the same time I'm sure you can see why this might be helpful as we start to combine complex numbers and trigonometry together. Final example, express z equals minus 1 minus I in modulus argument form. Again, start with a quick sketch. Minus 1 minus I is about here. Modulus, the square root of 1 squared plus 1 squared, gives us root 2. And the argument is a negative angle down here, but what I'm going to calculate is alpha here, which is pi by 4. So theta must be minus 3/4 pi. And putting it together, we get z is equal to root 2 times the cosine minus 3 pi by 4 plus I sine minus 3 pi by 4. And then we have the modulus argument form of z is equal to minus 1 minus I. That should be enough for you to have a go at the questions from exercise 1F and 1G if you have access to the textbook. And maybe I'll see you in the next video.